So previously we talked about just limits in general, but now we also want to discuss one-sided limits. And these are used usually with piecewise functions or when the domain of a function is restricted for some reason. And so just as a reminder, a piecewise function is a function that has different rules for different ranges of each independent part of that function, each piece. So if we were to look at this first example, where f of x is made up of two pieces, the first piece being x squared if x is bigger than 2, and x plus 1 if x is, or sorry, x squared if x is smaller than 2, and x plus 1 if x is bigger than or equal to 2. So in order to determine the limit for this function as x approaches 2, we have to use a two-sided limit, and we have to look at it from both sides, from the left and from the right, because there are two different pieces to this function. And so this is how we're going to write it down. We're going to say the limit as x approaches 2 from the left. So I'm just going to draw a little like number line just to remind you. So there's 2, and we want to approach 2 from the left. So if we're approaching 2 from the left, then that means that's any numbers that are less than 2. So we're going to evaluate the function x squared. And we're going to evaluate the limit of this function as x approaches 2 from the left of x squared. And so we're going to plug in our value and find out that that value is 4. And this is called the left-hand limit. And then we have to look at the other side. So here's our number line again. And this time we want to look at the limit as we're approaching 2 from the right. This is the right-hand limit. And so we're looking at any number larger than or equal to 2. And so we need to use the function x plus 1. And we plug in our 2 value, and we see that the right-hand limit is equal to 3. So now we have a situation where the limits or the value of the function at 2 is not the same. So if the left-hand limit and the right-hand limit are not equal, which they are in this case, okay, then this limit does not exist. So, and this is the notation for it. So if the limit as x approaches a from the left of some function is not equal to the limit as x approaches a from the right of the same function, then the limit of x approaching a of that function does not exist. However, if the limit of x approaching a from the left of a function equals some value, and that value is the same as x approaching a from the right, then the function has the limit as x approaching a, it has a limit, and that limit has the same value. So let's try an example. Okay, so let's look at the limit as x approaches -1 from the right of this function. So in this particular case, we'll just draw this graph really quick. This is a square root function, and it's been moved over 1 unit to the left. And so it doesn't make any sense to try to approach this limit from the left. There's no values there. So we're only going to go from the right for this one. Okay, so the limit as x approaches -1 from the right, I'm going to plug in my value, and I'm going to see that the limit is approaching 0. Example 2. Okay, so in this case, we can draw our graph again. We have the absolute value function, and it's been moved down 1. So in this case, we can approach this from the left and the right. So we're going to have to evaluate both options. So we'll start with our left-hand limit. So the left-hand limit, as x approaches 0 from the left, I'm going to put in 0 minus 1, and that'll be -1. And then the right-hand limit is going to be very similar, except I'm going to be approaching 0 from the right. Okay. And because because the left-hand limit equals the right-hand limit, I do have a limit. So as x approaches 0 of x minus 1, my limit is -1. Okay, let's try a more complicated example. So we have this piecewise function where it's composed of 3 parts, and the domains are less than -2, from -2 to 1, and then greater than 1. And so we want to figure out if there is a limit and what it is at -2 and at 1. So we'll start with -2. So the left-hand limit as x is approaching -2 from the left. So that means -3 towards -2. So that means I'm going to use this function. So I need to use 2x plus 3 and plug in this value that I'm approaching. And I'll see that this limit equals -1. Okay, let's try the next one. So the right-hand limit of x approaching -2, now from the right. Okay, so now I'm approaching -2 from -1, so I'm going to use this function, -x plus 1. -1 plus 1. Oh, sorry, -2. Okay, -2 is +2 plus 1 is 3. Okay, so here, -1 and -3, that's not the same, so this limit does not exist. Okay, let's look at the next one. The left-hand limit of our next one as x is approaching 1 from the left. So again, that's going to be this function, -x plus 1. So here I'm getting a 0. And then let's do this last one in green. Okay, so now my right-hand limit as x approaches 1 from the right. Now, so these are any numbers bigger than 1, so I'm going to use this function. Plug in my x value, which is 1. And this one will also equal 0. So now we can make a concluding statement here that the limit x approaching -2 of f of x does not exist, but the limit of x approaching 1 of f of x is equal to 0. So by determining the one-sided limits for piecewise functions, that's how we can determine if they are continuous or not, if the function is continuous. Okay, so by definition, a function is continuous at a if the limit as x approaches a of f of x is f of a. So there must be 3 things that must be true. So first off, point A has to be in the domain of the function. So if it's asking for a limit of a value that is outside of the domain, it's automatically not continuous. Secondly, the limit must exist. So the left-hand and the right-hand limits must be the same. And thirdly, the value of that limit must be f of a. Okay, if it fails any of these 3 conditions, then we would say that the point has a discontinuity at a. Okay, so let's look at this last example. So we have this function and it has 3 pieces, and we want to know if it's discontinuous at any one of these points. So we're going to have a look at where it could potentially become discontinuous. So the first spot is going to be at -1. So we'll start by finding the left-hand limit as x approaches -1 from the left. And in order to do that, we're going to use the first piece of the function. Okay, so -1 squared is 1, but negative that, so -1 plus 3 is 2. Okay, so there's our first piece, the first limit. And now we'll find the right-hand limit as x is approaching -1, but we're going to go from the right. So this is this function. And well, that has a given value of 1, so I don't even need to do anything. That equals 1. And so already I know that this condition here, this limit does not exist. So the limit as x approaches -1 does not exist. Therefore, the f of x is discontinuous at x equals -1. Okay, so I already know that -1 is a point of discontinuity. Okay, my next option might be at 1. So I'm going to start with the left-hand limit as x approaches 1 from the left. Well, if that's it, okay, so this again already has a set value, so it has to be 1. So the value of this function is 1. So that's is what it is. And then my last one will be the right-hand limit as x approaches 1 from the right. So this is any number bigger than 1. So I'm going to put in 1 squared plus 2 times 1, and that's going to be 3. And 3 does not equal 1. So also here, the limit of x approaching 1 of the function does not exist. Therefore, the function is discontinuous at x equals +1. Okay, so for practice, you've got homework page 27, number 1, 2, 4 through 7, 10, and 12.